Alright, so in this video we will discuss alternating groups, which are a very special type of subgroups of the symmetric group, which is the group of permutations on n symbols. Recall that any permutation can be written as a product of transpositions in many different ways. For example, let us consider the permutation 1, 2, 3, 4, which we can rewrite as 1, 4, 1, 3, so this way, then that way, right? And then 1, 2. So this is written as 3 transpositions. Okay, now we can take the same permutation and we write it as a product of 5 transpositions. Why? Because if you have 1, 4, 1, 3, and then 1, 2, we can multiply this by the identity permutation. But the identity permutation can be written as 1, 2 square, 1, 2 times itself. Why? Because 1, 2 is its own inverse. It's an element of order 2. Right? So then this shows that there is no unique way of writing a permutation as a product of transposition. However, there is something quite remarkable which happens here. The parity of the number of transposition is actually a constant. Meaning what? It's not a coincidence that we have 3 here and 5 here, and then 3 and 5 are both odd numbers. It's not a coincidence. So what we later prove is that the number of transposition which occur in the decomposition of a permutation can either be even or odd, but never both. This is quite important. All right. So in order to prove this, we need to develop a new tool. And for this reason, we introduce a polynomial called the discriminant. So think of x1, x2, and xn as n variables. And construct the polynomial x1 minus x2, x1 minus x3, all the way till x1 minus xn, and then x2 minus x3, x2 minus x4, all the way till x2 minus xn, and you keep playing this game until you can no longer. So the last factor will be xn minus 1 minus xn. So a shorthand notation for the discriminant is the following. We use this is the symbol for product, just like this was used for sum. We use this for product. So we take the product of all xi minus xj, and we make sure that I is always strictly less than j. However, I and j are both in between 1 and n. Okay, so this is our shorthand notation. And then if given an arbitrary permutation sigma, we introduce something called the sigma discriminant. And the sigma discriminant is obtained by modifying our original discriminant. So the sigma discriminant is also a polynomial obtained by simply taking the product of x sub sigma I minus x sub sigma j, where I and j are running through all possible elements in between 1 and n, but we want to make sure that I is always strictly less than j, just like we did when we introduced the discriminant, right? So the sigma discriminant is an auxiliary polynomial obtained by suitably modifying our original discriminants with sigma. Now, as we've seen earlier, any permutation can be written as a product of R many transpositions. So let's write sigma as tau 1 times tau 2 all the way till tau r, where each tau k is a transposition. Now, to determine the sigma discriminant, we need to take a look at the action of a transposition, right? So let tau be a transposition, which is acting as follows. Tau is essentially swapping k and l, and without loss of generality, let us assume that k is less than l. Now, one of the factors of delta has to be of the form xk minus xl, and the corresponding factor in delta tau will be x tau of k minus x tau of l, which is precisely xl minus xk, because tau swap k and l, and that is the opposite of xk minus xl. Now let us take a deeper look at the other factors. So the factors of the type xi minus xj, where I and j are not in the set containing k and l, will remain unaltered. Now all other factors can be paired as plus or minus xi minus xk times xi minus xl. Now the sign which is occurring here is determined by the relative position of k, I, and l, right? Now, for such pairs, the corresponding factors will be computed as follows. We'll have plus or minus plus or minus x tau of I minus x tau of L times x tau of I minus x tau of K, which is, now remember that tau fixes I, right? So that will be plus or minus xi minus xk times xi minus xl. And that's exactly the same as the corresponding factor in the discriminant. So this shows that in other words, such pairs are also not altered in the tau discriminant. Thus, when tau is a transposition, delta tau is essentially equal to the opposite of delta tau. Now, if we write sigma as a product of R many compositions or transpositions, then it must then be the case that the sigma discriminant will be -1 R times the discriminant, right? Because you have, each time you have a transposition, you are introducing a new negative sign. You have R many of them, so you will introduce R many negative signs. Okay? So then we'll say that the sign of sigma is 1 if the sigma discriminant is equal to the discriminant, and we'll say that the sign of sigma is -1 if the sigma discriminant is the opposite of the discriminant. However, it is not clear that this function is well defined. How do we know that it's not possible for the sign to both be plus and negative? That is something that we need to clarify. So how do we know that sign is a function on Sn? But let's put that to the side for now, and let's try to maybe understand a little bit what this discriminant is. Let's consider the case when n is 3. Then in that case, the discriminant delta x1, x2, and then x3 is x1 minus x2, right? x1 minus x3, and then you move to 2, x2 minus x3, and that's it. So this is essentially a polynomial of degree 3 in 3 variables. Of degree 3 in 3 variables. This is a multivariable function. Now, let's suppose we pick sigma to be the transposition 1, 2, and we want now to compute delta sigma of x1, x2, and then x3. Well, it will be x sigma of 1 minus x sigma of 2 times x sigma of 1 minus x sigma of 3 times x sigma of 2 minus x sigma of 3. Now, remember that sigma is going to send 1 to 2, 2 to 1, and is fixing 3, right? So we'll get x2 minus x1 times x sub 2 minus x sub 3 times x1 minus x3. And this can be rewritten as the opposite of x1 minus x2 times x1 minus x3 times x sub 2 minus x3. And this is the opposite of the discriminant of the discriminants when n is 3. Okay? Next. So we'll say here that the sign of this transposition is negative 1. Again, we can't, it's not clear whether the sign is a function or not. This is something that we'll clarify later. Now, let's find the sign of the transposition 1, 2, 3. To this end, what you will have to do is you write 1, 2, 3 as 1, 3 times 1, 2. So you have 2 transpositions here, right? So you'll say that the sign of 1, 2, 3 is negative 1 square, which is 1. Now, let sigma be a permutation, and let's suppose that you write sigma into a product of transpositions. And in the first case, you have R many transpositions, and in the second, you have S many transpositions. And then let's compute the sigma discriminant. In the first case, we'll get that the sigma discriminant is going to be negative 1 R times delta, right? And in the second case, we'll get that the sigma discriminant using this decomposition will get negative 1 S times delta. But this has to be negative 1 R times delta. And since delta is a polynomial, we can find values at which is non-zero. So then by dividing by those values, we'll get that negative S must be negative 1 power S is negative 1 power R. And because we have that, then S and R must have the same parity. That means that S is so S and R are either both even or they are both odd. So that tells you right away that the number of factors that is occurring in a transposition decomposition of a factor of a permutation, is may vary, but the parity of such number is a constant. the parity of the number of factors in a transposition decomposition of a permutation is a constant. So this tells us that the sign function is the sign, so that means that sign defines a function on Sn. Okay. Now we'll say that a permutation is even if it can be written as a product of even number of permutations. And we'll say that a permutation is odd if it can be written as a product of an odd number of transpositions. And these concepts are well defined at this point because we know that precisely only one of these can occur. Now there is the murky case of the identity, right? Because the identity is the permutation which essentially says everything to itself. So you can write it as 1 1 2 2 and let's say 1 2 and then 3. For example, this here is an example of the identity permutation. It says 1 2 1 2 2 2 and then 3 2 3. And usually we don't write one cycles, right? So we'll just often write the identity permutation as follows. But notice that if you take any two cycles has order 2. So because it has order 2, then any two cycle combined with itself will be the identity, which tells us that then by definition the identity is an even permutation. Let us consider the following permutation, which we can regard as an element of say S5. Then notice that so 1 goes to 2, right? Let's see here. We have that 1 goes to 2. 1 goes to 2, but 2 goes to 3. So that tells us that we can write sigma as 1 3. Now let's look at 3. 3 goes to 4. What about 5? 4. 4 goes to 5. And 5 goes to 1. So this is a 4 cycle. Now we can rewrite this 4 cycle as 1 5, 1 4, and then 1 3. And so this is written as a product of 3 transpositions, which then shows that 1 2 3 4 5 1 2 is an odd permutation. What about gamma? Well, we can write gamma as 1 3. So let's see here. 1 goes to 3 and then 1 goes to 2, right? And then 4 5. So gamma is also an odd permutation. Now let's take a deeper look at S3. S3 contains the following elements. It contains the identity. It contains the following 2 cycles. It contains the following 3 cycles, 1 2 3 and 1 3 2. Now there are 3 even permutations, right? Can you identify them? Well, the identity, since the identity can be written as 1, 2, and 1, 2. The 3 cycle 1, 2, 3, and the cycle 1, 3, 2. And that's it, right? And then it contains 3 odd permutations. The 2 cycles, they're all odd permutations. Now, is it a coincidence that the number of even and odd permutations are equal to each other? The answer to that is to come next. Let n be a natural number n, and let us assume for now that n is greater than 1, because the case when n is 1 is very not interesting. And let an, by an, we mean the set of all permutations in Sn such that such a permutation is even. So an, also the alternating, this is called the set, this will later see that this is actually a group, so and it's called the alternating group. Now we'll prove that an is a normal subgroup of Sn, and in fact we'll show that the order of an is actually half of n factorial. So let us get started. An is endowed with the composition, right? So we want to prove that this is a subgroup. So clearly the composition of even compositions, it must be even. Just do the counting of the possible transposition that can occur, and you get evenly many. The identity elements can be written as 1, 2, 1, 2. Thus the identity is an even permutation. If you are given the following as an even permutation, its inverse, as shown here, is also an even permutation. Verify this. So we have closure under the product. The composition of 2 even permutation is even. It has the identity, and it's also closed under inverse. So an is a subgroup of the symmetric group. Now recall that we've seen earlier that if alpha is any permutation, and let's say this is supposed to be an, and sigma is an even permutation, if we consider alpha, sigma, alpha inverse, they'll have the same cycle structure, right? So, and because they have the same cycle structure, then that means that they have to have the same, they have to have the same sign, right? So given that sigma is even, then automatically by conjugating, the permutation obtained by conjugating sigma with alpha is also an even permutation. So this tells you that if you take sigma an, sigma inverse, the conjugate subgroup is contained in the alternating group, and this shows that an is a normal subgroup of Sn. Now let gamma be a map which takes Sn into the multiplicative group containing -1 and 1. This is an abelian group of order 2, which is in fact, it's easy to verify that this group here is isomorphic to Z2. So this is isomorphic to Z2. Next, we will define gamma of sigma as being 1 if sigma is an even permutation, -1 if sigma is an odd permutation. Now, for 2 permutations alpha and beta, one can verify that gamma of alpha beta is actually gamma of alpha times gamma of beta. So this shows that gamma is actually a group homomorphism. So now let's look at its kernel. Well, the kernel consists of all permutations which are even by definition, right? So it's the set of all sigma such that gamma of sigma is 1. This is precisely all even permutation. So the kernel of gamma is an, not A4. It's the alternating group An. Now, by the first isomorphism theorem, then Sn mod the factor group, this factor group Sn mod the kernel of gamma, which is Sn mod An, is in fact isomorphic with Z2, right? So that tells you that the order of the group SNAN is precisely 2. So now if you were to pick, let's say, sigma an element of Sn such that sigma is not in An, so you're saying that sigma here is an odd permutation, then we will get that the collection An and sigma An, so this is the set of all possible left cosets inside Sn. This will give us a partition of Sn. So the set of all left cosets gives us a partition of Sn. Now notice that An has, let's say, we don't know, m many elements, and sigma An is a coset of An. It also must have m many elements. So since the cardinality of An plus the cardinality of sigma of An must be equal to n factorial, and on one hand we have that this is 2m, which is n factorial, then this tells you that m must be n factorial over 2. So this shows that as a group the order of An is precisely n factorial over 2. So in summary, we have shown that An, which is the set of all sigma in Sn such that sigma is even. We've seen that An is a subgroup of Sn. In fact, it's more than a subgroup, it's a normal subgroup of Sn. And we have also seen that the order of An is n factorial over 2. So earlier we saw that A3, the set of all even permutations in S3, consists of the identity 1, 2, 3 and 1, 3, 2. So here, since A3 has order 3 and 3 is a prime number, then it follows automatically that A3 is actually a cyclic group which is isomorphic to Z3. So in this case, this alternating group is actually abelian and cyclic. And here's the multiplication table of A3. So I would like you to pause the video and to check this multiplication table for yourself. Now, so here is a homework for you. I would like you to write down a multiplication table for A4, and I would like you to answer whether A4 is an abelian group or not.